Hello, everyone. Thank you for joining us today. My name is Stefan Mabry, and I'm a computer science PhD student here at the University of North Dakota. I'm here with Lane Odenbach, a computer science undergraduate student, also from UND. Today, we're excited to talk to you about the longest job first CPU scheduling algorithm, what it is, how it works, and why it's significant in the world of computer science. Let's dive in. Let's start by introducing the longest job first CPU scheduling algorithm. At its core, this algorithm prioritizes processes with the longest execution time, as noted by the burst time of the process. The goal is to maximize resource utilization while ensuring that longer tasks are scheduled first, fully utilizing system resources while potentially delaying shorter tasks. The history of this algorithm is rooted in the groundbreaking work of Ronald Graham, whose 1969 paper, Bounds on Multiprocessing Timing Anomalies, addressed challenges in managing multiprocessing systems. Graham identified several anomalies that could occur in scheduling tasks across processors, including increasing the number of processors leading to longer execution times, relaxing task dependencies resulting in unexpected delays, and decreasing task durations, causing longer overall completion times. These anomalies highlighted inefficiencies in task scheduling known as the identical machines problem, where the challenge is to distribute tasks evenly across identical processors while minimizing the delays. The longest job first algorithm attempts to mitigate these issues by optimizing resource allocation through its selection process. The LJF algorithm operates as a greedy algorithm. It selects the longest available job at any given point, aiming to maximize resource usage while risking delays for shorter tasks. An important characteristic of LJF is that it's non-preemptive, meaning once the task starts, it runs to completion without interruptions. This lack of flexibility can lead to challenges, as shorter tasks may have to wait longer than necessary, which we'll explore later. Overall, the LJF algorithm demonstrates a trade-off between efficiency and fairness. Now let's look at the challenges, or the advantages and disadvantages of the longest job first algorithm as compared to other scheduling methods. Starting with the advantages, LJF is highly effective at maximizing resource utilization. By prioritizing long duration jobs, it ensures that the CPU is continuously occupied, avoiding idle time. This is particularly useful in systems where efficiency is critical and workloads are predictable. Another benefit is the reduced context switching. Because LJF runs each task to completion, there's minimal overhead from frequently switching between processes. This improves overall system efficiency by avoiding the extra time and resources required to save and restore process states. Finally, LJF optimizes predictable workloads. By focusing on long duration jobs, it can provide consistent throughput for jobs of similar size, making it ideal for environments with well-defined task mixes. However, LJF is not without its disadvantages, and these make longest job first an unsuitable algorithm for most scheduling tasks. One significant drawback is the starvation of shorter tasks. If long jobs continue to dominate the queue, smaller tasks may be delayed indefinitely, leading to fairness issues. Additionally, shorter jobs experience increased waiting and turnaround times. Since they must wait for longer jobs to finish, response times for smaller processes suffer significantly, which can negatively impact user experience in interactive systems. Lastly, LJF is prone to the convoy effect. When slow, long-duration tasks occupy the system, it creates a bottleneck that blocks other processes, hindering overall system flow. As we can see, while LJF has a clear strengths in efficiency and resource utilization, its limitations can pose challenges in systems requiring balanced task handling and responsiveness. Okay, now that we understand the advantages and disadvantages of the algorithm, let's explore some real-world applications and understand the types and tasks it's most suited for, given its unique characteristics and limitations. LGF is particularly effective in scenarios where long duration tasks can benefit from dedicated resources and uninterrupted execution. These are typically environments where resource heavy processes are common, and the focus is on maximizing efficiency rather than minimizing response times for smaller tasks. One such application is in cloud computing. In cloud environments, LGF-inspired strategies are often used to prioritize resource-heavy workloads, such as large-scale data analysis or simulations. By scheduling longer tasks first, cloud systems can achieve more stable and predictable resource utilization, ensuring that heavy workloads are completed efficiently. This approach minimizes idle time for high-demand resources, improving overall throughput of the system. Another key example is the big data processing centers, where massive data sets require extensive processing. LGF helps reduce wait times in these environments by focusing on longer running tasks, which are often the backbone of big data workflows. By ensuring these tasks are completed without interruption, LGF improves throughput and reliability, which is critical for large-scale data processing and analytics operations. Overall, while LGF has limitations in terms of fairness and responsiveness, these examples demonstrate its value in domains where stability and resource optimization and efficiency are top priorities. And now I'll hand it over to Lane to talk about the algorithm specifics and the visual implementation of the scheduling algorithm.
Thanks, Stefan. Let's get into how the algorithm works. The first step in the LGF algorithm is to add all incoming processes to a process table. This table stores essential information about each process, such as its ID and its burst time, which is the amount of CPU time the process requires to complete. Once the processes are added, we can calculate and record their burst times to prepare for scheduling. Next, the scheduler examines all of the processes currently in the table and selects the one with the longest burst time. Unlike other scheduling methods, LGF prioritizes processes that require the most CPU time, giving them precedence over shorter tasks. By doing so, it aims to complete long processes early in the schedule. In the third step, the scheduler allocates CPU time to the process with the longest burst time and allows it to execute fully. Once the process is finished, it is removed from the process table, clearing space and reducing the number of tasks left to be scheduled. Finally, this cycle of selecting the longest burst time process and executing it repeats until the process table is empty. At that point, all processes have completed execution and the system can return to an idle state or await new processes. Now let's get into the code for the visualization on the next slide. Using Manim, which is a Python library for mathematical animations, we can create an engaging visualization to demonstrate how the longest job first scheduling algorithm works. By scripting the LGF process in Manim, we can visually represent each step of the algorithm, adding processes to a table, selecting the processes with the longest burst time, executing it, and repeating until the process table is empty. This allows us to walk viewers through each stage, giving them a clear understanding of the algorithm's flow. A basic LGF script starts out by creating a process table as a visual array or a grid to represent each process and its burst time. Using this, we created some animated labels and boxes and populated this with the processes of varying burst time. As you can see, that is represented by config.jobs. And then we have an animation that shows the execution of this process by dropping the bar until it hits 0. This sequence loops, each time reevaluating the remaining processes in the table, selecting the longest, and then executing it. Finally, once all the processes have been executed, the script is done. Let's get into it with the visualization that this outputted. In conclusion, the longest job for a scheduling algorithm maximizes CPU efficiency by prioritizing long tasks, which help reduce idle time and ensures the processor is consistently engaged with substantial workloads. By executing processes one at a time and focusing on the longest jobs, LJF also minimizes overhead by reducing the frequency of context switches, which can improve throughput in batch processing environments. However, LJF has notable downsides, particularly the risk of task starvation for shorter jobs, which may be delayed indefinitely if long tasks keep entering the queue. Despite this, LJF may be well suited for cloud computing and big data applications, where high throughput and sustained processing for large resource intensive tasks is essential. Here is the citations. We mostly use Geek for Geeks, but we also used a few different papers to get some of the practical applications. And anybody can ask questions in the discussion board where we post this video, and we will answer those questions. And then get in contact with us. As you can see, our emails are right there. And there is Stefan's office location, and there is his LinkedIn.